Sessions zimekuwaje? Imekuwa fiti? Yeah, so we are going to be having our second session today. And we are going to be studying decision trees, entropy, and ensemble methods. It's going to be quite engaging and technical. We'll do quite some bit of math. And so I would like your engagement. I like my audience being interactive, so I hope hamta ninyamazia, sindio? Yeah, so just to kick off, so who has worked with decision trees before? No one who's worked with decision trees, forests, such stuff? Thank you. Don't worry. I'm not going to ask heavy questions. What do you know about decision trees? What do you know about decision trees? For those who worked with them, what are they? What do they do?
It's like a pattern of decisions where the intelligence split data sets. And then there are various methods given on the effect based on the purity of the tree.
Mm-hmm. Thank you. So it's a step of decisions in splitting a data set, isn't it? So we are going to okay. Awesome, thank you. To have access to the notes. You can follow along also on the notes, but they are more detailed. Yeah, so James has told us that it's decision trees. Yeah, so I'll borrow this. Sorry, I'm all over the place. Yeah, so I would like to motivate the whatever we'll be studying with this case scenario. So we've studied let me say linear regression, isn't it? We've been able to study linear regression, and I would also maybe extend it to classification for this case, isn't it? So let me ask, can we have a line that can be able to separate this data set based on the two classes? A linear line that can separate those two classes. Why is that? All attempts will, there's no way, in essence, that data set is not linearly separable. Look at that point. So that's one of the places where decision trees come in handy, where sometimes the data itself is not linearly separable. So you cannot draw a straight line or a proper boundary line to separate them. And there are many ways of solving this. We'll have SVMs, kernels and all that, but we'll not be studying that for today. We will be looking at the idea of decision trees. So ideally, this is a minimalistic example. We can have two perpendicular lines and sort of have four regions with two regions belonging to one class and two regions belonging to another class, isn't it? But then how do we arrive at this? How do we arrive at this? So ideally, this looks something like, these are our axes. So this is 0, 0.5, 1, 0.5, 1, and then we have our first point there, the dot, and then this other one is here. Sorry, the axis itself is not on the origin, so pardon me for that. So we have these lines that are able to do that, isn't it? Now, the question is, how are we going to determine that boundary that does that? So you will notice the first step is we ask ourselves a question, the x-axis. And the question is x greater than 0.5 altogether? So that becomes a boundary on which you make a decision. So that's the first boundary here. And if it's greater than 0.5, it falls to this side. If it's less than 0.5, it falls to this side, isn't it? But as you can see, it's still not pure per se. The classes are not separated clearly. Are we together? So that leads us to ask the next question. But rather, let's see the results from this. So one answer can be no, and then the other answer can be yes. So and that's why we have now the two classes, either this side or this side. But then we ask ourselves another question on top of that after each result. Is feature y greater than 0.5? Is it greater than 0.5? And if it's a no, then you notice we have is x greater than 0.5? No. Is feature y greater than 0.5? No. Then we have this point is classified right together. If we go to the next point, you will notice we now get the other class B, which is 0.01, because all of them are less than the x is 0, but for this one the y is on the other side. And essentially that's how a decision tree looks like. It's basically a question giving a result, and then based on that you keep asking more questions until the classes are much clearer or separated out together. I hope we were able to get the motivation for that. So essentially the lines or the branches become the nodes become questions, and each branch simply is an answer to a question. So at each point we are branching based on a question and a decision that we make on that. So a decision tree is a sequence of questions, each with possible answers, and finally ending in a decision. Quick note for those who've done electrical stuff, you'll notice that this case is motivated by an XOR, where they fall in the same class if the Y and the X are XOR. So for example, 0 XOR 0, what's the value of 0 XOR 0? 0 XOR 0. 0 XOR 0 is 0. 1 XOR 1? 0. So the same class. 0 XOR 1? 1. 1 XOR 0? 1. So that's an example of the XOR is not linearly separable in this case. Yeah, but then what makes up a decision tree, the anatomy of a decision tree? We are going to look at this, we are going to work out this example later on, but we have several nodes. So we have nodes, that's the first thing, and then we have edges, and the root node is the first question that we ask altogether. So for example, in our case here, what is our root node? What is our root node in the example that we've worked out? Yes, be loud, be bold. Yes, is feature x greater than 0.5? That's our root node. And then you will have other nodes along the way. And so other nodes along the way are subsequent questions that are asked altogether. And then the leaf node, the last node is called a leaf, where it's not a question. The decision has been arrived to. You get that point? So in this example, for example, you'll find here it's a y greater than 0.5. That's a node, but it's not a leaf. You get the point? And it's also not a root node, because it's not the first question that is asked. So so it's sort of a node in the middle. So it's a question on top of the other one. But then we get to the end, class A, that is 0, 0, 0, 1, 1, 0, 1, 1. Those are called leaves. Do you get that point? Then we have the concept of depth. Depth is the number of questions from the root to the leaf altogether. So let me ask you, what's the depth of this decision tree? The depth of this decision tree? 3. 2. Anyone else? Why 3? We have 3 nodes, but how many questions have we taken? How many steps? 2 questions. You get the point? So the depth of a tree is based on the steps we make. So it's like we are at point 0, we get to point 1, and then we get to point 2. So it's a number of steps that we've taken. It's not just the stops, right, together. So that's the depth of the tree. So the answer is 2, because it's a number of steps that we get there. Now, so ideally, depth controls complexity of a decision tree. The deeper the decision tree, the more complex it is. The shallower the decision tree, the simpler it is. Altogether. And you're going to see that later on. So the root node is the first question asked. Edge is a potential answer to a question. The leaf node is a final decision. The depth is the number of questions between the root and the leaf. But the big question, and this is what we are going to cover for this session, is this was a simple example. So for this case, both questions are equally significant, or they carry the same weight. But the question is, which question is more weighty? I don't know if you get my question. Like, not all questions are equally significant. Do you get my point? There's a question you can ask, and it can have greater impact in separating the class than another question. I hope you get my point. See, nimepoteza mtu. Are we together? The question is, which question do we choose first? So this example, we had two questions. So let's say we have 10 features. And they have, you have a question on each of the features. So the question is, which feature do I select as the first question to split my data upon? And the whole idea is we want to be optimal in the sense that I want to ask the question that gives me the most optimal result at each step in purifying and splitting the data. Did you get that point? So that is the question you're going to be looking at. So the big question is, what is the best question to ask at each step? Not all questions are equal. Some carry more information than others. Do you get that point? And you're going to see that very shortly. So what makes a good split? Which question should we ask first? So this is another example or another question to motivate that question. And let's say we are making a decision of whether we should go for a run or not, isn't it? Based on two factors, what and what? Temperature and rain. Sindio? What are the possible conditions of temperature? Hot or cold, isn't it? And what about rain? Yes or no? And then what's the outcome of whether we will run or not? Yes or no? So when you're building our decision tree, and this is, I will say, I don't want to call it a trivial example, but it's base case zero, a simple example. Now imagine you're scaling search to 100, or 20 features, and you have to choose the first question. So what you're going to be studying here is, how does the tree learn to ask the best question? How does it decide the best question to ask at each step? Are we together? And in essence, the question you're going to be asking is, what makes a good split? What makes a good question at each step of the decision tree? So we have two candidate questions here. Is it hot or is it cold, the temperature? Is it raining or is it not? And the whole idea, as we have said, is a good question always splits the data so it becomes clearer and more predictable. So at each step, there should be, if the data set is mixed, if you have like squares and circles, a good question will, so let's say 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So let me add a few. So we have like 11 objects here, isn't it? Or 11 samples here. And there's 2 classes. A good question ideally will sort of make it that we have somewhat, we get like out of the 6 circles, we have like 5 together and maybe a 1 square, and then the other side is like maybe the 4 squares and maybe one circle. It's more clearer compared to something that splits into like 3 circles and 3 squares and 3 circles and 2 squares. It's still mixed. You get that point? So the question that does this kind of splitting is better than the one that will do this splitting. Do you get that point? You will see this is 6, 5. This is 6, 5, isn't it? That it's 6, 5, 6, 5. But the constitution of each of the classes is different in that this class is pure, and these 2 classes are pure such that obviously this is a square class. Obviously this is a circles class. But if I ask you which class is this, you cannot really tell me because it's 3 squares and 3 circles altogether. So I hope you get that with the point I'm driving at. So the question is, how do we learn, or how does the tree learn to ask the best question or optimally at each step? And yeah, so a good question splits data into groups that are purer. Most examples in each group belong to one class, as we have seen. A bad question produces mixed and predictable groups that don't help distinguish class. So the measure of how mixed a group is, how mixed it is, how unpredictable it is, how unclear it is called entropy. All together. Now, entropy comes from the idea, people who've done thermodynamics. What Tripoli, Poleni? Today I'm on your case. What is entropy in Tripoli? How you understand it? It's okay. I have not done Tripoli, but I have a notion. This idea that things tend to be more from order to chaos, as it was, isn't it? There is no clarity. Sort of things tend to become unclear and unclear. That's the idea. So higher entropy means that a class or a sample is unclear. You get that point? And entropy is lower when things are clearer. So, for example, this split, the one that we did with five circles and a square, the entropy is low. But the one that has a lot of mixed stuff and things are not clear, the entropy is high. Altogether. So, essentially, it uses this measure called entropy to be able to determine which question is better to ask and how it performs. I hope you're together up to that point. Kuna mtu tumepoteza? Okay. So, and people will call entropy surprise, and we will maybe going to see how that comes about. But let's say you have a bag of 100 red marbles and zero blue marbles. So you have a bag here that has 100 red marbles. How surprised will you be if you put in your hand and drew out a red marble? How surprised will you be? How surprised will you be? There is no, I mean, you expect it. You get that point. So essentially, and you see, this group is totally pure. So lower entropy or zero entropy means zero surprise. It's deterministic. It's expected. The probability is very high, and so we are not surprised when the event occurs. Do you get that point? But when the probabilities are low, so now imagine if we have a bag of 1,000 marbles, and 999 of them are blue, but one is red, and then I pick out the red. How surprised would you be? Very surprised. Look at that point. Sorry, it sort of beats the question again. That group is I will say is pure because it's 999 against 1. But the whole idea is the probability of you getting a red ball, one red ball, the only one among other 999 that are blue, is surprising. It's like winning a lottery or something of sorts. You get that point? So that's the idea of surprise. So you will not be surprised at all because the outcome is expected. It's sure bet. Observing a fully predictable draw gives zero information. So, and what we're building towards here is deriving the measure of entropy. We want to see how does entropy come about. How do we rigorously or mathematically formulate it from the principles that we are laying down. And let me just list them down here as we go along the way. And there's going to be some math here. So we have noticed that, one, the first characteristic of the measure of surprise or entropy is as probability increases, what happens to surprise or unpredictability? It decreases. And therefore, information also decreases. If you tell me you have a bag of 100 marbles and then you picked one marble and it was red, how much information have you given me? I expected it. Get the point? So I really don't get a lot of information. So ideally, the first characteristic we want of this is the surprise for probability of 1, whatever is inside there, the x is probability. Are you together? So x is probability, and probability is in the range of 0 to 1. It's a range of 0 to 1. So we want a function such that when the probability is 1, the surprise is what? 0. Do you get that point? And then, because as probability increases, surprise reduces. Conversely, when probability is reducing, what happens? Surprise increases. You get that point? But again, we will not get to 0 in itself. We want to take the limit. So as we are approaching, so the limit of f of x as x approaches 0 will be what? Infinity. So the lower the chances of something happening, the more surprised we are. Our surprise is always increasing. Do you get that point? So that's the first characteristic. So we are looking for a mathematical function that will give us, first of all, this characteristic, which is the first one. So basically, all that we have been discussing conceptually or intuitively about surprise and probability, the first thing, we formulate it rigorously or mathematically this way. So this is simply saying whatever we've just discussed, but mathematically. I hope you're able to see that. But then, the second thing is, if you have two events that are independent, are you together? And you are able to get information about each of them, how should that information correlate? It should be additive. Let me give an example. So if I know, so let's take the case for a coin and a dice. So say I have heads or tail here, and then here I have 1, 2, 3, 4, 5, up to 6. What is the probability of me getting a head on a fair coin? Let's say a fair coin. Probability of me getting a head on a fair coin? Yes? Aha, 0.5. Silio. What is the probability of me getting a 6 on a fair dice? 1/6. All together. Now, are these two events independent? Yes, they are independent, isn't it? There's no influence of one affecting the other. So what is the joint probability? Let me say, probability of the coin being head is 0.5, isn't it? The probability of the dice being the dice being 6 is 1/6, isn't it? Now, what is the probability that I have the coin as head and the as 6? What is that joint probability? What do you do to those two values? We multiply them, isn't it? So we'll have the probability of being head, this guy being head and this guy being 6, will be 0.5 times 1/6, which is roughly 1/12. All together. So that's speaking in terms of probability. All together. Now the question is, when we come to information, how do we want, when we receive those information, how do we want it to behave? We want it to be additive, because the one is not multiplying the other or any other thing. It's just one point of information and a second point of information. Do you get that point? Or the elements of surprise, they are adding to each other. So that leads us to a second characteristic that tells us we want a function that when I'm looking, so f is the measure of surprise here, or the measure of entropy here, such that when I get the entropy or the surprise of a joint distribution or a joint probability, it is the same as adding the surprise of each of the events. Do you get that point? Do you get that point? I feel like I've lost people. Are we together? Let me repeat this, because this is very important. It's leading us somewhere. So if let's take this example of a coin. So again, remember that surprise is correlated to probability, isn't it? Now, when we want a joint probability of a coin being head and a dice being 6, we multiply the probabilities, isn't it? So if you want to measure the surprise or the entropy in that case, which is our function f, we simply do f of probability being head and 6, and we get the value, whatever that may be. But we are simply saying we want this function to have such a characteristic that the surprise I get from this function will be equivalent to me getting the entropy of the probability of head alone, and getting the surprise of the probability being 6 alone. And when I have those two, I can add them. that these two, this side and this side are the same. You get that point? So the second characteristic we get here is that point, that multiplying and then getting the surprise is the same as getting individual surprises and adding them. Then quick question, which function do you think has this characteristic? Well, when you multiply two numbers and feed it to that function, it is the same as feeding each individual number to the function and then adding them. Let you think for a moment. Let me write it here a bit clearly. Because, personally, I've struggled to understand entropy, but I came to realize that studying it from first principles really helps you to get the intuition of why things are happening. I could have easily have given you the formula for entropy directly here, but I feel it will not be as helpful. So I imagine a function, let me simplify it here, function where a times b is equals to the function of a plus b. What function behaves that way? Yes, logarithms. Do you remember logarithms? That the logarithm of a number of a times b is equals to the logarithm of a plus the logarithm of b. Do you get that point? I hope we're together. So a candidate probability for our function f is a logarithm function. Are we together? But there's a caveat. So log AB is equals to log A, log B. We use base 2 because information computer-wise is measured in bits. And then the other thing is, remember, we said that when the probability of an event being is 1, what is the level of surprise? 0. Do you get the point? And the logarithm of 1 to any base is always what? 0. Do you get that point? So logarithm is sort of correlating to the characteristics of information or of entropy or the level of surprise that we've been studying. But there is something that we need to do. Log to base 2 of 1 is 0. But remember, we said that our limit of this function as x approaches 0 should be what? Infinite. Do you get that point? As you approach to 0, the limit of that function should be infinite. But the limit as x approaches 0 of this function log is what? Negative infinity. If you plot the log function, I hope I remember it correctly. It should be something like this, with this being 1, because the log of 1 is 0, isn't it? So for logarithm, as you approach 0, the logarithm function approaches negative infinity, isn't it? Now, we want it to be such a case that as we approach 0, the logarithm function approaches infinity, goes the opposite direction. What do? We multiply by negative 1 to reflect it. So our function will sort of go this way. Look at that point. And essentially, it's shown by this formula. If it's negative infinity, we can simply multiply by negative 1, and then we will have negative log to base 2 of 1 is 0, so that is maintained. And then this other side, then we have its infinity. So we have then that our function, f of x, is negative log to base 2, or whichever base you choose, of x altogether. Now, that is the function that is used to measure the surprise of a single event, the unpredictability of a given event altogether. And I hope you can see how that naturally arises from the conditions of the measure of surprise from probability. Do you get that point? So I could have given you this slide and told you f of x is negative log to base 2 of x. But I find the intuition to be helpful so that when you'll be relating with a function, you'll be remembering, oh, this is why this is so. Okay, so remember x is probability in this case. Now, but you will remember in probability, how do we get the average in probability? Average of a given value. Let me draw something here. Sorry, there's a lot of probability here in statistics. So let's say we have a table. I don't know if you did these tables for those who've done probability and statistics, where you will have a certain value x, blah, 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 blah. and then you have probability of x, blah, 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 blah. How do you get the expected value, or rather the average? If you have x and the probability of x, how do you get the expected value? Yes? When you have x and px, exactly. So in each individual case, we multiply x by the probability of the occurrence of x. Look at that point. So x times p of x. Look at that point. So it sort of gives weight to the probability, so that you don't overestimate one. I don't know what example I'll give here. So no, let me just leave it at. So okay, let's do a coin that is not fair. A coin that is not fair. Let's assume we have a coin that is not fair, and the probability of it being head is I think I'm confusing myself here, but it should be, let's say, 0.75 times 0.25 altogether. Then you do several tosses, and you get head a given number of times. Let's say 5, and then you do this other guy, and you get this guy like even 7 times, weirdly. Sorry. So what you do is you multiply this guy times this guy, and then this guy times this guy. You weight them by their probabilities. Are you together? You don't just take their probabilities directly. The probabilities sort of are weight. So in the very same way, with surprise, we have to weight it by its probability. Are you together? To get the average. So we multiply x times negative log 2 base 2 of x, because the element of surprise is negative log 2 of x, isn't it? So, and x is probability. So we just multiply with x, which gives us that. But again, remember, x is the probability of the distribution, capital X. Sorry, this is just a notation thing. So x is px in this case. So essentially, then the whole entropy formula, and then as Leonard has said, we sum that for all possible values of x. Look at that point. So for every single x, we get its probability, and then we get its measure of surprise. Multiply those two things. Sorry, my notation is a bit inverse. That end should be on the other end. The slides were a bit hard to fix on that. But essentially, probability times the element of surprise for all possible values of x from 1 up to n. And then when you sum that up, you have the measure of entropy for a given sample that you have. I hope you get that point. So ideally, every time the tree is making a decision, it is doing this calculation. And it is a mathematical formulation of the intuition we've just been discussing about determining which question is the most important. Look at that point. So we are going to work out an example here, and you're going to see practically that example of temperature and rain. So let's begin with this example of the one that we had of 100 bags. So if we have 100 red marbles and 0 blue marbles, what are the probabilities and what is the entropy? Let's work that out. What are the probabilities? Probabilities of getting a red marble? 1. Probability of getting a blue marble? 0. Altogether. Then what are the entropy? What is the entropy? I mean, what is the total entropy? So, and I want us to work this out before I show you the next slide, which has a formula. So the probability of picking red is 1 because it's 100 over 100. The probability of picking a blue marble is 0, isn't it? Now remember the formulation of entropy. We said h of x is equals to negative summation of from I is equals to 1 up to n probability of xi times the log of probability of xi, isn't it? Now let's go step by step. The first xi is red, isn't it? What is the probability of red? 1, isn't it? Times, what is the log of 1? 0, isn't it? We are coming to that. And then the next x, remember it's a summation, so it's negative here, and it's a summation, plus What is the probability of blue? 0. What is, and then the logarithm is log of 0. Are we together? Now, we are going to come to that in a moment. I know questions may be rising in your mind already. So, what is 1 times log of 1? What is 1 times log of 1? 0. Why? Log of 1 is 0. So, this is 0. Are we together? Now, a caveat to our function of h of x, 0 times log of 0 has an issue of being undefined. Are we together? So h of x can be defined. There's a convention that this will be 0, ideally, because if the event does not occur, then it's basically 0 together. That's one intuition. But more rigorously, mathematically, you can define h of x to be 0 when x is equals to 0. Otherwise, it is whatever function we gave there for x greater than 0. You get that point? So this is called, I don't know if it's a step function, but it's a function where you divide by the probabilities, by the possibilities of input. So if the input x is 0, the result is 0. If it's anything other than 0, between above 0 and obviously going up to 1, then our formula applies. So this will be what? 0. You get that point? 0 plus 0, negative of 0, 0. So what is our entropy? Do you get that point? And we realize that the measure of surprise of me picking a red ball or any outcome from there is 0. And that's the example that we have there. So let's do a 50-50 split and see what entropy you get from there. So let's say we have the probability of picking a red ball. Sorry. Probability of picking a red ball is 50%. Probability of picking a blue ball is 50%. What will be the entropy values? What will be the values and what is the entropy that arises out of that? So let's go step by step. As equals to this is h of x. So probability of being red is 0.5, and this is 0.5, isn't it? Let's go back to our formula. X1. Our x1 is red. So what is the probability that it is red? 0.5. And then times log of 0.5. All together. And then plus, what is the probability of it being blue? 0.5. And then times log of 0.5. All together. And then the whole thing is put in negative. All together. No. Who can tell me the value of that? 0.5 times log of 0.5 plus 0.5 times log of 0.5. I see people pulling up their calculators. It's okay, you can pull up your calculator. But let's do it this way. 0.5 times log of, this is base 2, by the way, this is base 2. A half plus 0.5 times log of base 2 times a half. What is log to base 2 of a half? What is a half in terms of the powers of 2? It's 2 raised to negative 1, isn't it? A half, 2 negative 1 is a half, isn't it? So it's 0.5 times log to base 2 of 2 to negative 1. Take that to the other side, negative 0.5 times log to base 2 of 2. What is log to base 2 of 2? 1, isn't it? And then our answer here is negative 0.5, and here it's negative 0.5, because it's the same thing. So negative 0.5 plus negative 0.5 is what? Negative 0.5 plus negative 0.5. Negative 1, isn't it? This is negative 1. But there's a negative out here. So our answer is what? 1. Do you get that point? So essentially, this split has the highest entropy. Do you get that point? So, and what gives the characteristic of this highest entropy? What is the defining characteristic of this distribution? Or of this case where we have a 50-50 split? It is balanced. So that means all the classes have equal chances. We cannot tell which will come best. It's highly unpredictable. Do you get that point? And therefore the element of surprise is high. Did you get that point? And this will happen for the dice. So essentially, and this is the other caveat, this is a side note. So when you have a coin, which is heads, tail, 50-50, and a dice, which is a 6, a 6, a 6, a 6, the element of surprise is higher, or entropy is higher for the dice than for the coin. And again, that's because the possible values are more. They are 6. It's evenly distributed, but it's 6 possibilities. But for the coin, it's just 2 of them. So the more the number of possibilities, the higher the element of surprise. Yeah, and so that's our calculation as we have seen. Our fair split is 1, and then the limit of log 0 is 0. So that's where we hold it. And then, so we have looked at the whole idea of entropy, and entropy essentially is also a measure of information, as we hinted. So if a bag has 100 red marbles and 0 blue marbles, and you take an action of picking a ball and you get the result, do you gain new information from the picking of the red ball? Not really. You get the point. But if I have a 50-50 split and I draw one of them, I gain some information. Are we together? So essentially, we want to be able to estimate when at each step we are making a decision, how much information are we gaining? Do you get that point? So at each step, how much information are we gaining? And how do we do this intuitively? So the tree calculates entropy before the split. So this is we have the distribution as is basically before doing the split, and that is what is labeled there as HS. HS is the entropy at the start. Are we together? Then we make a decision based on a given value of A. So let's say all the values of A, let's say for example it's temperature. Are we together? So it's temperature, hot or cold. Then what we do is we get the entropy for each of them, but we do a weight of the values of A. So for example, and you're going to see this intuitively, but ideally we do the entropy before here, before doing any split, and then we do the entropy after doing the split. That is, we are doing the entropy of each of the children that have arisen from the split. You get that point? So for example, if it's, we do not know they are going to run or not, and we have the total probabilities of run or not run, calculate that entropy. Then we make a split and say, okay, yeah, if the temperature is hot or cold, then we have these 2 children results. You get that point? And then we calculate each of their entropies. This is what HS is doing there. We add them up, but in adding them up, we do a weight. So sorry, this formula is not as clear. It's clear in the notes. We do a weight of the value against the total. So it's like a weighted sum of the same. Then we subtract from the initial entropy. And then we see how much information have we gained from that. And we make a decision based on that. So I want us to do this briefly. We're going to do this, and once we have done this, I think the bulk of the presentation will be done. So we will spend some time on this table to do a few things. So if you have a notebook, somewhere you can write, or if you can follow along on the board, it will be really nice. And maybe you can, as I wipe the board, you can be chewing on how that looks like. So essentially, we're going to, step by step, do a decision tree, and we are going to ask the question, at the first step, which question should we ask? Which is the question that gives us the highest amount of information for this table and for the decision that we are about to make, whether we will run or not run. Is it the question on temperature, or is it the question on rainfall? And how does that look like? So we'll begin with the first question, which is the temperature split. Are we together? But before we do the temperature, we have to calculate the start entropy. So remember, h of x is negative summation of p of xi log p of xi. Are we together? I is equals to 1 up to n. So, and our probability there is of whether we will run or not run. Get the point? So what is the first case scenario or first possible outcome of running or not running? The first is, let's say, is yes, isn't it? Now, what is the probability that we will run? How many yeses are there? How many yeses are there? 2 out of 6, isn't it? So essentially, it is negative of 2 over 6 times the logarithm log to base 2 of 2 over 6. That's the first one. The second option is a no. The probability that we don't run, obviously, is a remainder now, 4 over 6 times log of, remove this, log of 4 over 6. All together. I hope you're flowing together. Someone to do this quickly on the calculator. 2 over 6, log 2 over 6, 4 plus 4 over 6, log 4 over 6. What do you get? And then don't forget the negative. I hope you are crunching the numbers. Two over 6 log to base 2, 2 over 6 plus 4 over 6 log to base 2, 4 over 6. You have a number? Pardon? 0.2764. Okay. What do you get? But it seems to have a different answer. No, say it. Negative 0.5. What base are you using? Base 2. Okay. Anyone else? What did you get? 0.918. Anyone else? This is an interesting scenario. I almost thought I was wrong until someone mentioned the answer I had. Can you confirm? Have you multiplied with the weights? It's 2 over 6 times log to base 2 of 2 over 6 plus 4 over 6 times log 4 over 6. Have you done that? It's not log 2 over 6 plus log 4 over 6. It's 2 over 6 times log 2 over 6 plus 4 over 6 times log 4 over 6. And then you add that. And then get a negative. Try that again. It's 2 over 6. That's the probability here. Times the element of surprise. So it's 2 over 6 times log 2 over 6 plus 4 over 6 times log 4 over 6. Add those two, then get a negative. What did you get? But here, Mbogwa, I hear you. You are saying something? Mbogwa? 0.91? Everyone else is getting that? You gotten that? Okay. So the initial entropy is 0.91. 8 altogether. So you must never forget that weight. But I presume the guy who got negative 0.264 was doing base 10. So if you do base 2, I think she'll come to 0.918. So then the question is, when we split, what are the entropies of each subgroups when you split them altogether? So let's say we split on temperature. So the first possible split is a question of temperature. And we have the one section is the cold group, mornings, altogether. And 3 mornings and hot group is 3 mornings. So what is the entropy of cold based on whether we will run or not run. Are you together? I don't know if you get the point. We have a subset here. So let me go back to the distribution and show what I mean here. So we have this table, and we have split the table based on the question of temperature. Are we together? Whether it's hot or cold. So when you split by hot or cold, we get two sub groups. Are we together? And then we look at the entropy of each group on whether we will run or not run. Look at that point. So we take the first group of temperature is hot, and then do the entropy. Do we run or do we not run? Then we take the other temperature cold. Do we run or do we not run? Take those two entropies, then sum them up. Are we together? And then you go back and get the information again. I hope we are together on that. So, so we have the cold group, and the cold group tells us that we have three mornings and 2 yeses and 1 no. Are we together? So on that group alone, what are the possible outcomes first of all? Yes or no? Are we together? The probability of yes is what? 2 over 3, isn't it? So it's 2 over 3 times log 2 over 3. Are we together? We are calculating, we're using this formula. Don't forget, this is what we are running on. Plus, so remember there's a negative here always. Plus, so we're in this summation. The next possible outcome of a no, which will be here, is what? 1 over times log 1 over 3. Are we together? Someone to do that very quickly? But if you have some sharp eyes, I think you should have the answer already. What's the answer? 0.918, isn't it? These two are the same. This is 1 over 3, which is this. This is 2 over 3, 2 over 3, which is this. Are you together? Yeah, but you can do the calculator, it's that. Are you together? Then the other question is, what about the case when it's hot? What's the probability of a yes? 0. So it's 0 times log 0, which is what? 0. Are you together? Then we have, the other one is 3. So what is the probability of a no? We not run. 1 times log 1. What is log of 1? 0 times 1. So what is the answer here? 0. Are you together? Then what we do with these probabilities is the formula on information gain. So we are going to tie up these things together. So this is perfectly pure, and I hope you can see that the element of surprise is 0 because all results are no. So we do the weighted entropy. So ideally, there's no need to hide this. So it's 3 over 6, because there were 3 cold results and there were 3 hot results altogether. So we are weighting against that. So it's 3 over 6 and 3 over 6 times each individual entropy. You get that point? So it will be 3 over 6 times 0.918 plus 3 over 6 times 0 is equals to 4.59. Are you together? So this is the entropy after we have done the splitting. Do you get that point? So we had the question of do we run or do we not run? And we got an entropy of 0.918. Now we have decided, let's ask our questions on the basis of temperature. If the temperature is hot, what's the entropy of running? If the temperature what's the entropy of whether we'll run or not? If the temperature is cold, what's the entropy of that? Then we get the total entropy after splitting, which we have gotten is 0.459. Now, what is information again? Remember we said it is the difference between entropy after splitting and before splitting. So it's 0.918 minus 0.459. Therefore, what is information gain? 0.459. That's the information we gain when we split on temperature. I hope you're together up to that point. Now, if we go to rain, and you're going to do this very quickly. Okay, what is the answer here? Even without doing the math. Why is it 0? It's, pardon? The probability is 1. So the group is pure. Get the point? It's pure, it's predictable, it's fully sure. Hapa tunajua we will not run when it's raining. Then the other one is 2, 2. What do you think the nini is here? I think we have done this. 1. Why? It's even. It's 50-50. It's like the fair coin split that we did. Are you together? So there it's 1. You can do the math for that. So it's perfect 50-50. So and then we do the weighted entropy and the equivalent information gain. So the weighted entropy looks like 2 over 6 times 0 plus 4 over 6 times 1, which is 0.667. Then the question is, what is the information gain? We separate, we subtract, which is 0.918 minus 0.667. What is the information gain? So which is a better question? Temperature or rain? Which is a better question? What is the information gain on temperature? 0 point? What is the information gain on splitting on rain? So which is the heavier question? Which question gives more clearer results after the split? Temperature. You get the point? So what is the first question that will split on? Temperature. So the first question that the tree will ask is it hot or is it? Now that is what the tree does at every step. When it has a set of features and has questions to ask, it will ask that, it will look for the most important or most significant question, ask on that. Then at the next step, it looks at the remaining question, calculates the entropy, and does ask the next question, step by step as you go along. And the winner here is temperature. So what we have looked at is entropy, the idea of entropy, the idea of surprise, the idea of predictability, and the idea of information gain, which is how the decision trees operate. For me, it was quite fulfilling to be able to understand why logarithms are used and the intuition behind it, rather than just doing the math, having x log x. Yes?
So assuming that's the
Yes. Yes.
the entropy that we subtract from will it be the first the entropy that you calculated
Mm-hmm.
first one for all of them, or it will be the entropy for the second now the step that you
What do you think? If we take the third step, so the second step, you've done temperature, then you go to rain, and we want to see the information gain on rain. What entropy will we subtract from? Is it after splitting with temperature or before splitting with temperature? Yes? It's immediate, but what do you mean by that? Mm-hmm. At level 2. And why is that? Because already at step 2, we have made those choices up to that point. So our distribution looks that way. That is the entropy at that step. And the next step is a change from that case. Are you together? So not that it's not a question. So there's a big difference here. A subtle difference here. What we have covered here is a question of, we have probable questions and we want to be able to choose on which question. So it's a question of options. Are you together? But once we have an option and we choose that one, we make a step, then our new state, our new entropy is different. Do you get that point? Then from there, we have other options, now which we will compare against our current state. Do you get that point? Because the entropy of the system has changed based on the decision we have made. Okay, get the idea? Yeah, so feel free to ask any question, by the way. Thank you for that. Feel free to ask any question as we go along. Yes?
So, assuming that based on all the features that you have, assuming that on each and every question you ask the
Mm-hmm.
the tree have to do all the questions.
Pardon?
Like assuming now, because in this case you are considering the first question we create
Yeah.
first.
Yeah.
So assuming that the entropy for each and every sort of question you can ask based on the features, they are all the same.
Mm-hmm.
What does the decision tree do?
Okay. Maybe that's a case I will need to study. But anyone is free to answer. But the answer that comes in mind is most probably it will just choose one of them because there's no preference. But I presume that tells us something about the features in terms of their correlation. Because if their entropy is the same for all the features, then there's something it tells us about about the data set itself and the nature of the data set. But that's something worth exploring. I don't know if anyone has a thought on that. Yes? Please raise your voice. Mm-hmm.
Based on these midpoints, then you can use them as the questions that you are like this splitting points. And then check on the height. You select one with the height.
So his point is, you have the questions, and all of them have the same entropy, so the information gain is the same, because our starting state is x. Then all the questions have an entropy of y. Each of them have the same entropy. So ideally, the same information gain is across all the questions. So the question is, which question do you choose? And that's why I said my thought is one, either the tree will just randomly choose one, but back of your question, it seems to imply something about the characteristics of the features themselves. There may be some correlation, because it will be very interesting to see such a scenario. I don't know how it will pan out, but it would be interesting to see how that would look like. We're good? Okay, so yeah, so that's what it does. But, so there's a caveat. This is the foundation, the idea, that's the idea of information and the information gain we get after making each decision. But in practice, a library like a scikit-learn does not use the measure of entropy itself. It uses something called the Gini index, and we'll not look at that. I think the practical in the afternoon will handle that very, very well. And the Gini index looks like 1 minus the sum from 1 to k of the probabilities at each step squared, the probability squared. Now, the reason for this is the logarithm function in entropy is very expensive to calculate for a computer. Look at that point. The complexity of a logarithm function is very high. So the Gini index sort of will most often, if not always, arrive at the same, but it's faster. Look at that point. It's faster. So you'll meet scikit-learn uses a Gini index. But I think once you've understood the idea of entropy, I mean also understanding the Gini index will not be hard. But I find it very interesting that that is the case. Now, something interesting I noted when Batia was presenting on the log loss. What is the formula of log loss? What's the formula of log loss? Someone can check. A log loss is a binary classification, isn't it? So there are two probabilities, and both of them sum to what? To 1, isn't it? Now, what's the formula? You can Google it. Negative what? Y log P minus plus 1 minus Y log 1 minus. What do you see about this thing? From what you studied? Obviously, this is a probability of what? What is y times log y? Look at this. P times log. Do you get that point? This is y log probability of y. I mean, yeah, so y here and the linear are more or less the same, but they are weighted. But ideally, when you look at this, because our case is from 1 to 2, it is just split out that way. And the other case, obviously, the other probability, and again, if you see it's 1 minus y, again, it means they sum up to 1. Take that point. So ideally, this is the other term in it. So essentially, this is, again, it's entropy. So the log loss is a measure of entropy. Yeah, it tries to minimize entropy ideally. That's why it's called binary cross. entropy. So yeah, when Patty was presenting and then I saw that formula and I'd been preparing on entropy, I was like, oh, it's the same thing. So it's very interesting. So, but then, and I want us to wrap up because I see time is much spent. Then the question is, how do we know when we stop growing the tree? So we have had the case of 2 questions, but let's say your data set has 100 features. Do we ask all the 100 questions? Do we ask a subset? How do we know when to stop? Do you get that question? Because intuitively, you might think that the most ideal thing is to let the tree grow until it's fully mature. That means we've asked every question until we have a depth of 100 for 100 features. Are we together? But that's not often the case. Why? It may achieve perfect accuracy and it may achieve an entropy of 0. But that tree will have overfit and it will be very sensitive to all kinds of perturbations or noise. So if it sees new data that it has not seen, it will fail terribly. Why is that? It's been able to learn the noise and the outliers and has not generalized. Do you get the idea? Because you'll obviously realize that data is not always purely cleanly splittable. Sometimes you'll be able to split it, but you'll have like 1 or 2 elements of one class in the other side and some other elements in this other class. So the entropy will not be purely 0. So if the tree gets to a point where it is 0, most probably we looked at the example of XOR, but let me I don't know if I can think of a good example here, but let's say we have such a case, and maybe we have a decision tree that is trying to learn these features. And we let it grow to the fullest until it gets an entropy of completely 0. Most probably, you'll notice something weird. It'll have things that look like this. Most probably trying to match, so it looks messy because it's trying to capture everything in one class and the other in the other class. So it will have memorized and captured everything because of the growth of the depth. So you'll meet some questions that are hair splitting, like you'll see there's a question that intentionally tries to capture these and this. Well, obviously these are most probably an outlier, whereas a good decision tree will split on this even though 2 are here and these 2 are here. Do you get that point? So if the tree is allowed to grow entirely to the fullest, it will overfit and will not generalize well. So a tree has regularization hyperparameters, and these are some of them. One is maximum depth. That determines how many questions we can ask along the line. The other one is minimum samples per split. So we may have splits, so we ask ourselves, we don't want a split where, like for example, for that case, you'll meet the tree has split and maybe it has captured some four circles in one, some 3 circles in another one. But then there's a split that has only 1 circle. And ideally, most probably it's a circle from the other side. So it shows us that it's trying to overfit and capture the noise. So minimum samples can tell us, no, we need to split a node in such a case where the samples are a given example. That's for splitting. For leaf as well, minimum impurity decrease. So there are all those measures. And here's the correlation between depth, bias, and variance. So if the tree is very shallow, the bias will be high. It will not be able to capture the general dynamics of the data distribution, and the variance will be low. It underfits. So you must balance the depth for you to get a balanced bias and variance. A fully grown tree will have very low bias and very high variance. It will overfit. So depth is a very key knob or key hyperparameter in the definition of a decision tree. So here's a summary. I think I'll just pass over this very quickly. Nonlinear boundaries, like the orthogonal splits that we saw, it's interpretable because at each step it's a question asked and answers given, and we know why the question is asked because of the information gain. So it's very interpretable. We chose temperature because it has high information gain, and we can show the value for that by calculation. There's no feature scaling needed, handles mixed data. We are going to see that in other methods like boosting and bugging, and then a high variance. So small changes in training data can produce completely different tree. And this opens us to the next part. So you can read some of these materials. They are in the site. You can have a look at them. They help a lot in understanding better. So we have been able to look at a tree, and we are wrapping up. The main burden of the presentation is largely done. But there are a few points I want us to get as we close up. So the primary weakness of a single tree is that it is very unstable. A single tree is highly sensitive to even small variations, making it very unstable. So if a change in maybe even the sampling, for example, if we sample a certain way this time and we sample the next time the other time, the distributions and the entropy calculations will change because it's very deterministic. And so you'll meet certain perturbations to the data will cause it to change greatly. So this is we have to look at a means of giving stability to a decision tree, or rather a technique that we have looked at so far. So, and how do we do that? That's the idea called ensemble methods. What is the idea of an ensemble? An ensemble is, instead of having one tree, you have several trees. And there are two primary ways in which they correlate to each other, and you're going to look at that very, very briefly. And so the decision is not arrived at by a single tree, but it's an aggregate. I use the term aggregate intentionally, because the aggregate can be any function. But yeah, the decision is an aggregate of all the decisions, whether be it the maximum, whether be it the average, it depends. But the condition is that the errors of the tree must be uncorrelated, or they will not balance each other out. And then the idea here is, if we have 10 trees, one tree will be strong in a given area and weak in a certain point, and another tree will be, maybe strong where another tree is weak, And so when we do the aggregate, the weaknesses or the errors balance out. But if all the trees portray the same weakness, the same error, the same failure mode, then it is simply amplified. To get that point. So the one condition here is that the errors of the tree must be uncorrelated. When the errors are uncorrelated, the weaknesses of one tree are covered by the strength of the others. And so there are two questions that follow. How do we produce trees from the same data set whose errors or whose residuals are uncorrelated? And then the other question is there a more powerful aggregation strategy than averaging? And the first case is called bootstrap sampling. So what is bootstrap sampling? Bootstrap sampling is you train each tree on a slightly different random sample of the training data. From a training set of n samples, you draw n examples with replacement. So this is what happens. We have our training sample of, let's say, 1,000 points, isn't it? So we select a subset of n examples to train on it, each tree, but we do it with replacement. So we pick n from the 1,000, train one tree on that, repeat again with the same set of 1,000, pick another different n, So, and ideally this, because of replacement, we will have sampled multiple times and a few others will be left out entirely. So it sort of tries to even that out. Now, something interesting is with bootstrap sampling, and by the way, this is where, this was interesting when I also discovered it. It's something I discovered. I don't know if it's correct or not, but I think this is where boosting comes from. Either boosting or bugging, I'm not sure. But yeah, bootstrap sampling, boosting. Yeah, so, and ideally, when you draw n samples from an INI, the mathematical average approximates that 36.8% of the original data set will be naturally left out. And this number is actually, the number of excluded rows has a term. It's called out-of-bag samples. And the mathematics is very interesting. This is just a quick one. So probability of not picking a row A in a draw. So if we are picking n rows, the probability of picking a certain row, of not picking a row is 1 minus 1 over n, isn't it? Because they are equally possible of picking a row. So, and then after n rows, it's multiplicative. So 1 minus 1 over n. Now, if you take the limit as n approaches infinity, you get it's the inverse of the natural logarithm. This is an interesting discovery as well. If you remember calculus and the formulation of E, you'll notice that E was limit to n, limit as n approaches infinity, 1 minus 1 over n to negative n. But this is positive. It's 1 over E, and that gives us 0.3678. That simply tells us that the probability a given sample will not be picked As n tends to infinity, is at 6.78%. So however much you do that bootstrap sampling, 36.78% of the data set, roughly, approximately, not exactly, will be left out. And this provides a way of doing cross-validation on quality estimates without having a separate validation set. So they can submit each tree's performance on data. It never saw during training via cross-validation because of this idea called out of bug. So the aggregating, one possible way of aggregating is, so now we train k different trees on k different bootstrap samples. So we do the bootstrapping, pick n samples from an ini with replacement, do that k times and generate k trees altogether. And then having generated k trees on X, you take the majority vote. So the vote that has the majority is the one that wins. Do you get that point? Yeah. So this is sorry. Boosting does not come from bootstrap sampling. Sorry, it's bagging. Sorry, bagging. So it's bagging is bootstrap B aggregating bagging. So I hope you see that bootstrap aggregating. That's where the name comes from. Bagging. So, but trees can still be correlated, and even with bootstrap sampling, if one feature is highly informative, if one feature dominates the distribution, obviously, almost every tree will pick it because it's very dominant in the distribution. So even if we do bootstrap of n samples, most probably out of those n samples, the one feature that will stand out will be that one. So this is a case where also, even with bagging, the errors can still be correlated, and that leads us to random forests. I think many of us know random forests. These are just points I'm passing over, building on top of what we just learned. So we add a second layer of randomness on top of the one that we've looked at. And the idea here is at each split, the tree may look only at a random subset of features. Typically, it's usually square root of p. So again, we don't let it look at all the features. We constrain it to a given set of features, which typically should be square root of p, where p is the total number of features. This forces the trees to find different mathematical paths to the answer, causing heavy decorrelation. So if different trees look at different features, then they will not have the same information, and so the mathematical formulation at arriving the answer will be different. So individual trees are unstable, but random forest is incredibly robust, and every tree can be trained in parallel. So ideally, you can have 100 or 1,000 trees being trained at the same time because they are not dependent on each other. I know GIS heavily uses forests for many things. So this is bagging in summary, bootstrap aggregating, parallel training, reduces variance dramatically, free validation via out of bug evaluation. But it does not fix bias if all the trees fail on the same case. Average preserves the mistake. So if the same failure mode is on all the trees, the bias is not fixed. So the last thing I want us to look at is boosting, and then we look at the summary, and then we close it. So, but bagging doesn't fix bias in case there are such issues as we've looked at. Is there a better way of looking at it? So this is where the idea of boosting comes in. And what does boosting do? Boosting simply means we have one tree, we make decisions on it, then we calculate the residual, the error, the failure of that tree. Then the second tree corrects the mistake of tree one, learns from the residuals of the first tree altogether. So the idea is, rather than building trees independently in parallel, boosting builds them sequentially. Each subsequent tree aims to minimize the error of the previous tree, forming a chain. So you have tree 1, and then tree 2 tries to correct the errors of tree 1, tree 3 tries to correct the errors up to tree 2, all the way until the final ensemble is arrived at. So that's boosting. Possible algorithms that are out there for boosting, it's ADA boost. So it starts with equal weights for all training examples. You train a shallow tree, can be depth 1, which is called a stump, can be, but a bit shallow, so it can be 2 or 3, depending on the features you have. Then with classified examples, receive higher weights for the next round. So that's where adaptive boosting comes from. So the ones that are misclassified get more weights. So the future trees put more emphasis on those. And then the next tree is trained on the reweighted data set, forcing it to focus on hard examples. And the final prediction, weighted vote of all the trees. But there's a more modern idea called gradient boosting. It frames the task as a gradient descent in function space. Instead of reweighting examples, each new tree is trained to predict the residual errors of each of the current ensemble. So instead of trying to reweight the sample, so tree 1 has done the results, made the decision, and then based on the failure modes, we reweight it, and then the tree 2 learns that, that's adder boost. But instead of that, gradient boosting doesn't do reweighting. Instead, it predicts the residuals, which are the errors of the current ensemble. So this is what it looks like. So if we do m-1 step, the next m step will be where f of x will be the function at that step. So we take the f at the previous step, then we do a learning rate times the output of the new tree based on x, and that will be trying to be trained on the residuals or the errors of the previous ensemble. So it's sort of building on top. So at every step we are building, it's recursive, ideally. And so some modern implementations, XGBoost, like GBM, CutBoost. I've personally worked with CutBoost. It's very good for categorical values without encoding. You don't have to encode things. So this is good for data that has very many categorical values or categorical features. Like GBM, histogram-based, default growth, dramatically faster, XGBoost is regularized. You can have these notes, they are in the NINI, so I won't emphasize so much on them. So bagging versus boosting. Bagging fixes variance, instability of a single tree, fails if trees systematically face on the same point, best with deep complex trees. Boosting fixes bias, each subsequent tree corrects the prior errors, can overfit if not regularized, best for shallow trees, that is trees that have a high bias and low variance. So this is a full picture. Decision trees can be trained in a single pass, random forests can be trained in parallel, but gradient boosting has to be sequential. So decision tree, an individual decision tree can have its own weaknesses. Random forests fixes variance, gradient boosting fixes bias. The risk for which is overfitting. Random forest is a bit stable, so slightly it can underfit, but it's quite stable because of the wisdom of the crowds, as they call it. And then overfitting for gradient boosting if it is not well tuned. Interpretability, decision tree is high because it's logical at each step. Random forest medium, because each tree makes its own decision, then you sort of get the majority voting something. So it may be hard to get the interpretability. Gradient boosting is low because it operates like typical neural networks in some degree, because you're learning on the bias, not the bias, on the residuals, the errors, that is. So yeah, key hyperparameters, maximum depth, number of estimators. So for random forest, you can decide the number of estimators, the number of trees you want to be in the forest to be making decision. You can have like 10 trees, 100 trees, 20 trees, 1 trees. That's a hyperparameter to tune it. Maximum of features, same thing with gradient boosting. Although for gradient boosting, now you have learning rate. We are going to look at learning rate in future when we do neural networks. I think there'll be a session on Thursday. Yeah, so baseline exploratory, it's best for that. Robust production baseline. Maximum accuracy and training tabular data. So the rule of thumb, random forest is usually a strong first choice because it's robust. It requires minimal tuning and gives feature importance scores immediately. You can choose gradient boosting if you want extra accuracy and if you are willing to spend the time. There is some time investment in tuning it. XGBoost and like GBM are good options. CutBoost is very good for categorical values. Real-world applications, credit scoring. So you want to take a loan. Also atafanya nini yako, if else, age, ameoa, hajaoa, ana salary ya ngapi, anaishi wapi, sijui nini, and all that. Detection, when you make transactions and all that. Medical diagnosis on some parts. So yeah, that's basically it. And sample summary, I will not look at that. You can go study. I think I've talked a lot. Where to go next? You have all these resources. They'll be in the website. You can have a look at them. Yeah. So trees ask a question that clears the most uncertainty. That is entropy and information gain is used to quantify this. That's what we studied. Bagging, average many decorrelated trees to cancel out instability and reduce variance. Boosting, you chain trees sequentially, so each one corrects the mistakes of those before it. And so the architecture follows data. So data informs the architecture of whatever you choose. And this again will also be seen when you're doing neural networks. So this is a hint towards that. So the math behind architectures is informed by the characteristics of the data. So yeah, so it's time to have some fun. So I thought to create something interesting here. How many have ever played a Kahoot? I want us to play some Kahoot in the next 2 minutes as we finish. Yes? No, it's for fun. It's for fun. I don't have prizes. Amo, you want to play for prizes? The prize is information gain. Yeah, so you can go to Kahoot. We have a few questions just to jog our minds. I know it's been a bit heavy. I know the math has not been easy, so it's a good way of toning down and relaxing. The pin is 424-9978. Kahoot.it 424-9978. Sorry, this was prepared in a rush, so some images that are not be there, but I hope we'll be able to learn a few things. Kahoot.it 448. Are people joining? Nickname. Who's calling himself nickname or herself? Kahoot.it. Just go to Kahoot.it, and then it'll ask you for the pin. The pin will be 424-9978. 424-9978. 424-9978. You want to see the information gain and the entropy from the lesson. I think we'll be able to calculate that, Cindy. Hey, me, Francesco. Haha wakodi. Okay, it's okay. Okay, mtataka kuandika jina yake. I think I know someone here. I think I know who's written a given name here. It's okay. Najua watu kadhaa hapa. Are we all in? Kuna mtu tunangoja? You're not in, but you're getting in. You're getting in. We start? We can start? We can start? Kuna mtu yote anataka tumgoje? Okay, let's start. So I'll have no control of this. I'll just stand by and watch. I hope it will be clear from the projection. I think 20 seconds are a lot. Sanya, what's up? Hey, Pole. Are you still in? The faster you answer, the more scores you get. Answer quickly. True or false? True or false? Ah. This is very high entropy. People did not gain information from this class. A straight line can always separate an XOR pattern. XOR pattern is the first thing I drew there. And you say it's not linearly separable. So it's a false. Let's see. Three more people, two more, okay. Yeah, it's a leaf, it's a leaf, it's a leaf. I know there is any question, so I know there is any question. This should be easy and fast. 100 red marbles, 0 blue marbles, what's the entropy? How mixed is it? How pure is it? The answer is 0 because it's very pure. So yeah, sorry. I know entropy can be confusing from the definitions. Who's fleek? Which function did you pick to measure surprise? Or to measure entropy. Surprise is entropy. Surprise is entropy. Okay, yeah, sorry. Surprise, entropy, information, more or less the same. Two more people. Ah, perfect. 13, it's 1. It's entropy of 1. I think we did that there. Two seconds, 1 second. Ah, okay, yeah, it's a better question. A better question is equal to high information gain. Naona nikaa Flickr ametolewa juu. Don't be too fast. Fast and furious, eh? One more guy, one more person to answer. Well, the entropy is not so high, but there seems to be some level of confusion. Undefined by convention. I think it's even there. 0 log 0. It's 0 by convention.
What's the answer supposed to be?
0. Yeah, by convention it's supposed to be 0. How attentive, which question was the winner? Leonard no uko na rain. Who's the other guy who's put rain? Uko sawa? Who has put rain?
But you see, you're saying the correct one is pointing red. So you see, once you see red, it's like it's a wrong one.
Oh, that's why you're surprised. Yeah, no, temperature is the correct one. Ticked. Flick is flicking this thing. 5 people. I think we need to redo this class. Letting a tree grow until every leaf is 100% pure is always a good idea. Is it a good idea, really? It's the last thing we've discussed here about overfitting and regularization. Flick. Hiyo swali imetenda watu, eh? Random forest. You can still redeem yourself. Which one is it? Oh, okay. Gini index. So entropy is logarithmic. Gini index is it's quadratic because it's a sum of squares of probabilities. People are loading. It's maximum depth. It's primary dial. I see. People are reclaiming themselves. Zero entropy on this one. Everyone has gotten that one. It's 36.8%, correct. Don't worry, I had to put decimals, otherwise watu wangejua tu yenye iko na decimal ndio answer. How far? Which question are we number? Yeah, false. Random forest can be trained in parallel. Remember, random forest does, there's a second level of randomness where you sample square root of n samples, and you can do that in parallel and train different trees. No, square root of p features, sorry. Square root of p features. Oh, I've given you the answer. Yeah, it's random feature subsampling. Square root of p features. So does not randomize the labels, does not randomly delete trees. It samples, you have p features, it will choose square root of p, it will subsample that. You can do that very effectively in parallel. Oh, tables are changing drastically. Hapa inakaa entropy iko juu. You notice we studied bagging first and then we studied boosting later. So most probably automeka variance bias. I think you confused the two. Underfitting, overfitting. Maybe that is also a correct answer. But still the order is wrong. The order is wrong. It should have been underfitting, overfitting, not, yeah, because bias is underfitting, so it's still wrong. Are you together? Hey, the first shall be last. Okay. The entropy here seems also to be very high. In gradient, remember gradient boosting uses gradients, and the gradient is always operating on residuals or the errors. Are you together? Yeah. The other one was the one that Ada boost. Ada boost is the one that is trained on the reweighted data set. So gradient boosting works on gradients. And it specifically learns the ninis of the previous one. Hata nimewapea answer au hapa sijawapea answer. It's a trick question. Yeah, that's why I said it's a trick question. Okay. Sawa sawa. Poleni. The entropy is high. I think I'll correct that. No, but the order has not changed. So information gain is 0. So I think we should be wrapping up. Yeah, you remember random nani amepata wrong? Pole. So random forests can parallelize because you can subsample root P features at the same time and train X different forests trees at the same time. Boosting, you always have to get the residuals of one to train the next. Residuals of one to get the next. So it's always sequential. And I think we are done. So the podium, number 3, who ni nani? Sorry, ina sauti. Who's number 3? Haijaonyesha jina. Who's haha? Number 1 ni nani? Okay. Jemo. Who's sure? What's sure? Who's number 3?
Me.
Batia. What was your name?
Swift.
Oh, you are Swift. Yeah. Oh, that's nice. Yeah, but I hope you have. Yeah. This is a general 65 correct answers. Hii ndio watu wameumia sana. Which other one? These ones are the hardest questions. But yeah, thank you guys. I hope you've learned something. I hope it will help you along the way and you're ready for the afternoon session. So we will call it at that and have a nice day. I hope no one, anyone with a question? We all good? Sawa sawa.